So in the previous lecture, we arrived at what we call as of course at the towards the end of the discussion on the Bayesian decision rule, we arrived at the decision rule in the form of the computation of a likelihood ratio, capital lambda r. It's a function of the received random variable, which we had defined as the ratio of the two likelihoods, which is the conditional density function of R having received H1, or having the conditional density function of R given that H1 is the true hypothesis, and in the denominator we had the conditional density function of R given that H0 was the true hypothesis, and the decision rule was like this. So whenever this likelihood ratio was more than the ratio of these probabilities, where P0 is the probability of occurrence of hypothesis H0 and P1 is the probability of the occurrence of hypothesis H1. So whenever this was more than this ratio, the likelihood ratio was more than P0 by P1, the decision rule is such that it declares H1 as the true hypothesis, otherwise it declares H0 as the true hypothesis. Now we'll take an example quickly, and we'll see how the decision rule works. We'll take an example which has close similarity with a real life situation. Suppose we have a binary source of information. I have just put it as a binary data source. So being a binary data source, we know that the output could be any one of two symbols. And as we did earlier, when we discussed the general picture, when we started our discussion on developing the decision rule, we had hypothesis H1. So here also we have the two hypotheses. H1 is when the output of this binary data source is, say, bit 1. Hypothesis H1 is the output is bit 1. And whenever the output is bit 1, whenever the binary data source output is bit 1 or the hypothesis is bit 1, this data source gives out a voltage 5 volts. So S1 in that general picture corresponds to 5 volt here. And when H0 is the hypothesis, bit 0, let's say, and the corresponding output, let's say 0 volt. So whenever bit 0, hypothesis H0 is true, bit 0 is the output. Remember, hypothesis is the way we identify which of the two bits were the output. So when bit 1 is the output, we say it is hypothesis H1, and at that time 5 volts is given out by the data source, and otherwise it is bit 0 and 0 volt is given out. And it gets, in the course of its journey towards the receiver, the noise random variable gets added as earlier, and in this case, let's say that the noise is zero mean and Gaussian distributed. The noise is zero mean and Gaussian distributed, and and hence, of course, we know if it is zero mean and Gaussian distributed, the probability density function will be 1 by root of 2 pi sigma, where sigma square is the variance, sigma is the standard deviation, e power minus n square by 2 sigma square. So this is zero mean Gaussian distributed noise which gets added. So the density function of n is this, and this is known in advance to us. And the received random variable is R. There is a decision. This is the receiver. Inside that you have a decision device or a decision rule in place, maybe in the form of a circuitry or whatever it is, as I said earlier. So this block represents the receiver inside which you have a decision taking mechanism. And the output of this is the decision. The output is the decision, which could be bit 1 or bit 0, and as earlier the receiver can make errors which we hope will be occasional, and it will be occasional provided your decision rule is well designed, in the sense, of course, we saw that under the circumstances, under the assumptions that we know certain things which are realistic assumptions, the decision is based on the Bayesian decision rule, which is the optimum one under those circumstances. So now we have, when H1 is the true hypothesis, received random variable is equal to, instead of S1 plus noise, we have now 5 volt plus noise. And when H0 is the true hypothesis, what we receive is 0 volt plus noise. And this being the case, since we know the density function of noise, to be Gaussian, we know it is Gaussian and zero mean. And when H1 is true hypothesis, a constant 5 gets added to this. When you add a constant to a random variable, what happens is that the mean of this will be shifted. So when you add 5, the originally noise is of 0 mean. If you add 5 to this noise random variable, the mean of this will become 5 and the variance will remain unchanged. Density function will remain unchanged, in the sense the density function will still be Gaussian. The distribution does not change. Similarly, in this case, since you are adding 0, what you have received is nothing but the noise. So now we can write down the conditional density functions. Density function of received random variable when H1 is the true hypothesis will be equal to, as I said, when H1 is the true hypothesis, what you receive is a constant 5 volt plus a Gaussian distributed noise which is of 0 mean. So the conditional density function of the received random variable when H1 is the true hypothesis will be Gaussian distributed with mean 5 and variance same as what we have for the noise. So density function of R given H1 is the true hypothesis will be 1 by root of 2 pi sigma e power. Now mean will be 5, so minus of R minus 5 whole square by 2 sigma square. So you can see that this is nothing but a Gaussian density function with mean 5 and variance sigma square, and that is the density function of the received random variable when H1 is the true hypothesis. Similarly, we can write the density function of R when H0 is the true hypothesis as equal to, when H0 is the true hypothesis, we saw that what you are receiving is nothing but, because since when H0 is true hypothesis, it is 0, the output is 0, what you receive is just the noise. So density function of R given H0 is the true hypothesis will be nothing but the density function of noise itself, because what you are receiving is noise itself. So that will be 1 by root of 2 pi sigma e power minus R square by 2 sigma square. So we have these two conditional density functions, which means we can straight away write down the likelihood ratio and proceed with the decision rule. So we can straight away write down the likelihood ratio here. So likelihood ratio is capital lambda R PR H1 divided by PR H0. So this divided by this. So when I do that, I will skip some steps because it's a simple thing. This you have to divide by this. These two will cancel, and you will end up with e power. So remember, this is divided by this, e power minus r minus 5 whole square by 2 sigma square, that is divided by this. So when you divide it by that, you can use the law of indices and write it like this. You can write it like this, and further simplification is possible in the sense we can group the terms here, and we can write this as, probably I can I'll write it here, e power minus 1 by 2 sigma square r minus 5 whole square minus r square. So you can see that minus 1 by 2 sigma square is taken out as a common factor, and you have r minus 5 whole square minus r square. Since you have taken minus out, this becomes minus r square, and this can be expanded further. So I will just write the expansion here. R square gets cancelled, and there will be a 25 because of the squaring of this, and there will be a minus 10r. So minus 10r plus 25. R square and r square gets cancelled. So you will have minus 10r and a 25. And this is now compared with P naught by P1, H1, H naught. That means in our case, H1 is, hypothesis H1 is that the bit 1 is the output, and hypothesis H0 is bit 0. So this is how it looks like when you have a situation where the data source, binary data source, sends 5 volt for bit 1 or 0 volt for bit 0 and 0 volt for bit 0, and the noise is Gaussian with 0 mean, and we are in sigma square. This is how the Bayesian decision rule is going to look like. Now the presence of an exponential term here, e power something over here in the likelihood ratio, prompts us to take the natural log of this. If you take the natural log of this, what happens is you take the natural log of the likelihood ratio, which will result in 10r by 2 sigma square minus 25 by 2 sigma square natural log of P naught by P1 bit 1 bit 0. Now this is called as the, this we will call as the log likelihood ratio. We call it as the log likelihood ratio, or in short LLR. So we call it as the log likelihood ratio. So if you take the log likelihood ratio, the decision rule becomes like this, and now we see that the decision rule, the computation involved can be brought down if we could retain, keep r on one side and take all the other terms on the other side. So if I do that, I will get 10r minus 25 bit 1 bit 0. So for short I will write like this: 2 sigma square natural log P naught by P1. And further we can write this as 10r 25 plus 2 sigma square natural log P naught by P1 or R has to be compared with 25 by 10 plus 2 sigma square by 10 natural log P naught by P1. So this can now be written as, this is 5 by 2, that is 2.5, 25 by 10 is 2.5, and this will be sigma square by 5. So you can now see that this is how the Bayesian decision rule appears in this case. So all that the receiver has to do is, having received a value R, it has to simply compare it with this. This can be already computed, and because you know sigma square, receiver has knowledge of the noise variance, because receiver has knowledge of the density function of noise. Receiver has knowledge of this, and these others are just numbers. So the receiver can have this sort of threshold. We can call this as a threshold now. The receiver can compute this threshold and store it, and then having received R, it has to just compare it with this threshold and then take a decision. If it is more than the threshold, declare it as 1. If it is less than the threshold, declare it as 0. So a question may come now, what if it is equal to the threshold? If it is equal to the threshold, you take a decision either 1 or 0, but be consistent with that. So whenever, probably I can put like this now. If R is greater than 1, declare it, R is greater than this, declare it as bit 1. If it is less than or equal to this, declare it as bit 0. So this is how the decision rule looks like in this case. And further, if P naught is equal to P1, as it is in most of the, I can probably confidently say 99% of the binary communication systems, P naught is equal to P1. And if that is the case, this ratio will be 1, and this entire term will vanish if P naught is equal to P1, because ln of 1 is 0. If P naught is equal to P1, the entire thing vanishes, and you are just left with comparing the received random variable with 2.5, which incidentally lies between 0 and 5. So you have to simply set a threshold between 0 and 5, which is 2.5, and then take a decision based on whether the received random variable is more than that or less than that. If it is more than that, declare 1 as the transmitted bit, otherwise declare 0 as the transmitted bit. So this is how you can see that the noise being Gaussian helped us in bringing down the amount of computation. Otherwise, we would have had to calculate the likelihood ratio every time we receive R. We would have had to calculate lambda R, capital lambda R, and then compare it with the term on the other side, which would have been P naught by P1. But the noise being Gaussian, we have some advantage in the sense that we could go for the log likelihood ratio, which helped us in isolating R on one side and keeping the other terms on the other side, the other terms which could be computed in advance on the other side, and just compare the received random variable with that and take a decision. So this is an example as to how one can, or how the decision rule looks in practice. So with that example, we now move on with our discussion on the basics of signal detection and estimation from the context of digital communication systems, of course. Now, what we have to understand is that in a real life digital communication system, the receiver does not receive a random variable R. Instead of that, it receives waveforms, it receives continuous time waveforms. So what I mean by that is that, let me redraw that block diagram and try to explain through that block diagram what I mean when I say that the receiver is receiving continuous time signals and not just a random variable. So as earlier, we have the binary hypothesis source, And when H1 is the hypothesis output, earlier we saw that it was giving out a measurable quantity S1. Now, in a real situation, what the binary hypothesis source gives out when hypothesis H1 is true, say for example, could be a signal like this, a continuous time signal like this, a time dependent, a time varying signal like this. And for H naught, when the other hypothesis, it's a binary hypothesis source still, when H naught is the hypothesis, it may be giving out another signal S naught T, which is different from S1T. So earlier we assumed that S1 and S naught was the output of the binary hypothesis source when hypothesis H1 and H naught respectively. But now in a more realistic scenario, a practical case, it will be a waveform S1T for one of the two hypotheses. That means, again, if you think in terms of a binary communication transmitter or a data source, a binary data source, a binary information source, for bit 1, say for example, it may be a waveform which it sends out, and for bit 0, it may send a different waveform. And these two waveforms will be distinguishable, of course. And consequently, in the course of its propagation, in the course of its travel, the course of these signals travel, depending on whatever is the hypothesis, some particular signal is sent, and in the course of its propagation towards the receiver, we have a noise waveform getting added. It is not a random variable anymore which gets added. Earlier we had n getting added to S1 or S0, but now it is no longer a random variable. A random process gets added. A noise process gets added. And as earlier, if we are to apply the Bayesian decision criteria, knowledge of the statistical distribution and such things about this noise process will be known. And similarly, the receiver will have perfect knowledge of S1T and S0T, but the receiver will not be able to. The task of the receiver is then to find out which of the two hypotheses were transmitted. But it will have knowledge of S1T and S0T. And consequently, at the receiver side, so if I call this as a receiver now, inside which you have the decision rule and all those things, you will not be receiving R as earlier because a time varying signal is given here, a function of time, a signal is sent here, and what gets added is a random process. So what you receive will also be a random process T. You will be receiving a random process. It will not be receiving a random variable anymore. What you receive will be a random process. Now, we can say that when H1 is the true hypothesis, the received random process is equal to S1T plus NT. So what you receive will be the sum of the transmitted signal for hypothesis H1, the output signal for hypothesis H1 and the noise random process. And for H0, received random process will be made up of the sum of these two. So this is, and of course, these signals will all be valid. You need to define a time interval. You cannot have this signal forever. So when hypothesis H1 is true, say from time 0 to capital T, a signal S1T is transmitted. And this T, the duration T, is called as the observation interval for the receiver. So the receiver has to observe this signal for a duration T and then take a decision as to whether S1T, that is hypothesis H1 was true, or S0T, that is hypothesis H0 was true. So in digital communications, this T is called as the signaling interval, and 1 by T becomes the symbol rate. So again, if I have to connect it with a digital communication system, a real life binary digital communication system, say for example from time 0 to capital T, the output of the hypothesis source may be bit 1 and signal S1T may be transmitted, and then from T to 2T, that is the next duration T, bit 0 may be the output or bit 1 itself may be the output. So if it is bit 1 itself, then again S1T is transmitted. If it is bit 0, then S0T is transmitted. This is what I mean by the signaling interval. And in terms of the detection theory, we say that it is the observation interval, the observation duration. So you are seeing this received random process for a duration T, and then you have to take a decision. So this is a more realistic scenario compared to the previous one, wherein we were assuming that some S1 measurable quantity is given out, or S0, and then it gets added with a random variable, the noise random variable, and you receive a random variable. And then in that case, we have seen how the Bayesian decision rule works. Now, this being the case, this is a more realistic case. We have to have some method with us so that this received random process can be expressed in terms of random variables faithfully. Faithfully in the sense without losing any information that this carries, which is going to help us to detect which hypothesis was true. So without losing any such information which is going to help us to find out which hypothesis is true, we must be able to express this in terms of random variables. If we can do that, we'll be able to apply the Bayesian decision rule which we developed in the previous lecture. So towards that end, we have to discuss a bit of signal representation. So to understand how this received random process can be expressed in terms of random variables, we need to discuss a bit of signal representation. Now, suppose we have a signal S of t. Suppose we have a signal S of t, which is of finite energy, and is of duration t. It's of duration t. Say from 0 to t. It is existing from the signal S of t is there from 0 to t, or say t1 to t1 to t1 plus t. So we will take this t1 as 0. So a duration t, say 0 to t. And it is a finite energy signal, which means that this will be finite. The signal is of finite energy and it is of duration t. Now, if you have a signal like this, it is possible to represent this signal as a series expansion, as I am about to write here now. S1 phi 1t, S1 into phi 1t, where S1 will be a constant, phi 1t will be a function of time defined in this same interval 0 to t, that is of duration t. Remember, St is also of duration t and it's of finite energy, plus S2, which is another constant which we call here on as coefficients, phi 2t, and so on and so forth up to Sn phi nt. So this n can go up to infinity, or it can also be some finite number. So this means that the signal, finite energy signal, which is of duration t, can be expressed in the form of a series I is equal to or rather k, we'll stick to k. K is equal to 1 to n s k phi k of t. Now here in this series representation, this is a series representation, so it is, you can clearly see that we are expressing the signal s of t in terms of a linear combination of phi 1t, phi 2t, phi 3t, and so on up to phi nt, in terms of a linear combination. And the s1, s2 up to sn, these are the way we are weighing these functions and adding them up. These are the coefficients, expansion coefficients. Now phi kt, k equal to 1, 2, etc. up to n are orthonormal. These are orthonormal functions. Now what we mean by orthonormal is that they are orthogonal, mutually orthogonal, and also they are of unit energy. So if I arbitrarily take phi I t from this, where I is from 1 to n, if I take any one of these signals which we are linearly combining to get s of t and calculate its energy. Remember, these signals are also defined in the same interval 0 to t as the signal s of t. This will be 1, so of unit energy. That accounts for normal, and orthonormal means of unit energy and orthogonal. Now what we mean by orthogonal is that if I take any two, if I take any two from this, say phi j and phi k, if I take any two where j is not equal to k, I take any two from this 1 to n, I take any two, phi j and phi k, j is not equal to k. Say for example, j could be 1, k could be 3. And then if I take an inner product, this is complex conjugate. If I take an inner product, the result will be 0. So these functions are complex in general. That is why I have taken a complex conjugate. The signal s of t can also be complex in general. So if you take an inner product like this of any two functions from this set, the inner product will be 0 as long as the functions are not the same. If the functions are the same, then the result will be 1, because if j is equal to k, you are going to end up getting something like this. So this is the reason, or this is what we mean by a set of orthonormal functions. They are orthogonal as well as their energy is 1, their norm is 1. So this together can be expressed as equal to the result of this integration. We can capture both of these, that is orthogonal as well as the unit energy thing can be captured by writing this as equal to delta j k, where this is called as the Kronecker delta, which is defined as delta jk is equal to 1 if j is equal to k, is equal to 0 if j is not equal to k. So we can express it in this way, and this single expression tells us what we mean by orthonormal set of functions. You take any two from that, perform an integration like this, that is, you take the inner product, the result will be this. The result will be 1 only if the two functions are the same, and then in that case the inner product is only going to give you its energy, and otherwise the result will be 0. So that means the orthogonality. So that's what we mean by orthonormal functions. Now when we express the signal s of t using this type of a series representation, the orthonormal set of functions that we use are called as a complete orthonormal basis. It's a complete orthonormal basis set, because you can see that the signal S of t is expressed by a linear combination of these orthonormal functions. So they act like a basis. They are of unit energy and they are orthogonal to each other. They act as a basis. You can compare this with elementary vector theory, and you know that any vector can be expressed through a linear combination of basis vectors. So we call this as a complete orthonormal basis, and it is possible to express a signal S of t through a linear combination of this basis. It is called as the series representation of the signal. And exploiting this orthonormality, it is possible to find out what should be or what are the coefficients S1, S2, S3 and so on up to Sn if we have the signal with us and the basis with us. So what we do is, let's say we have the signal S of t with us, which is of finite energy and of a certain duration, say 0 to t, and we have the complete orthonormal basis with us. That means we have all the basis functions with us. We have phi 1t, phi 2t, phi 3t up to phi nt, the required number of functions. Now if I do this, let's say j or k is okay. If I do this, remember we are trying to find out the coefficients. If I do this, what I am effectively doing is, when I do this, what I am effectively doing is the signal S of t, I'll express it as it's in its series representation. I will express it in its series representation S of t and when I take this summation along with this S, because Sj phi j summation j1 to n, Sj is a constant which we are yet to find out, but it's a constant. It can come out of the integration because integration is with respect to time. Phi j Sj integration with respect to time, phi j t, phi k conjugate t dt. And this result we saw just now, that this is equal to the Kronecker delta jk, and hence this will be equal to, so when you go through this summation, at some point of time j will be equal to k, and only at that time will this have a non-zero value which will be sk, because delta jk is 1. This is 1 only when j is equal to k. And when j is equal to k, what you get is S of k. For all other values of j, this is 0. So in that summation, except for S of k, all the other terms are going to vanish. So this is the way you can get the coefficient Sk, which you will be using like this. Along with other coefficients, you will add it up and get the signal S of t. So this is how we can find the coefficients of the expansion, of the linear expansion, or the coefficients of the series representation of the signal S of t. So from this we see that Sk, that is the kth coefficient, is obtained through an inner product of St and phi kt. So S1 is obtained through an inner product of St and phi 1t, S2 is obtained through an inner product of St and phi 2t, so on and so forth, till you need the required number of coefficients to represent your signal S of t. And the final takeaway from this discussion is that the final takeaway, as I said earlier, is that it is possible to represent a signal S of t purely with its coefficients. So let us say that we have a signal S of t, and we have, let's say, we need not worry for the time being at present as to where we get this basis from, but let's say we have the signal S of t, which is a finite energy in a certain duration it is defined, and we have a complete orthonormal basis set with which it is possible to represent this as a series representation. Let's say we have this available with us. Now we can express this signal S of t with only the coefficients. It is possible to express this signal only with these coefficients, because you know that this signal can be constructed with these coefficients if we could linearly combine these individual bases using these coefficients. So to be more specific, S of t is, as I have been telling all this while, so phi 1 to phi n is known. We are knowing it in advance. We are given the basis in advance. Signal S of t, we can represent that signal if we have complete information about the signal if we know this. Now this can be compared with the probably the more familiar vector spaces, wherein if we have a vector, we can express it using its coordinates given the basis, of course, given the basis, and if we have a vector, we can express the vector using its coordinates. Now if the basis changes, the vector does not change, but its coordinates will change. The vector, the entity does not change. It will have the same direction in terms of direction and magnitude. If you speak, it will have that same direction and magnitude, but its coordinates change when the basis changes. Similarly, the signal S of t with a set of bases like this, a complete orthonormal set or a complete orthonormal basis, will have a set of coefficients, and using these coefficients you can express this signal. If you go for a different set of complete orthonormal basis, then the signal can still be expressed like this, but its coefficients will be different. And how do you find the coefficients? The coefficients are found through an inner product of S of t and phi kt. So, but the signal S of t will not change. The signal S of t will have its own physical significance, its own physical existence, but its coefficients will change if you change the basis. And using this series representation, in fact, the key to represent the received random process R of t in the previous block diagram, the key to representing this in terms of random variables is there in this discussion. It is there in this series representation of the signals. So as I said, once we are able to express R of t, the received random process as random variables, we can apply the Bayesian decision rule which we developed earlier. So let's now take one simple example and try to understand the series representation. And also, once we express a signal S of t in terms of its coefficients for a given orthonormal basis set, it is also possible to show this signal as a vector in a vector space. So that we will discuss. We'll take an example and try to understand that. So moving on to the example, let's say that we have a complete orthonormal basis set with us with phi 1t as so phi 1t. This complete orthonormal set that we have is in the interval 0 to t. Phi 1t is like this: 1 by root t from 0 to t by 2 and minus 1 by root t from t by 2 to t. You can easily verify that its energy is 1. So if you do phi 1 square, you get 1 by t, 1 by t, and when you integrate that from 0 to t, you'll get the result as 1. And let's say phi 2t, that is the second function in the basis set, is this minus 1 by root t. And again, of course, it is till t. This is t by 2, and you can see that its energy is also 1. Similarly, we have phi 3, phi 4, and so on and so forth, about which we will not mention now. There are other such functions, let's say. So only two functions I will consider, two functions from that orthonormal basis set I will consider here. Now suppose we have a signal st which is defined in the interval 0 to t and which is like this: minus 1 from 0 to t by 2 and minus 2 from t by 2 to t. Let's say this is the signal s of t. Now, by virtue of the discussion, the previous discussion, we know that s of t can be expressed as a linear combination of the functions phi 1, 2, phi 2t, phi 3t, and so on and so forth. Series representation of s of t, that's what I mean. So this signal s of t can also be expressed in the form of a series representation using this orthonormal basis set, out of which two functions I have shown here. There are other functions. Let us now find out so the expansion is for our quick reference. I will write down the expression here. S of t can be expressed as you know very well by now, summation k1 to n can go up to infinity, sk phi kt, and sk is determined by, this was also explained, taking an inner product of st with phi kt, we get sk. So let's find out s1 in this case. So what we are trying to find out is, what is that s1 with which I have to multiply phi 1t and then add it to s2 into multiplied by phi 2t and so on and so forth. So let's find out what is that s1, so that we could represent this signal as a series representation using the orthonormal basis set that we are having with us. So s1, if I try to find out, s1 will be, using this, an integration from 0 to t of st. St is the function that we have with us, the signal that we have with us, and phi k conjugate t will be phi 1 conjugate t, and since phi 1 is a real function, I don't have to write conjugate because it's a real function. So if you conjugate, you get the same thing. So if you do this, you will get S1, and this will be equal to, from the interval 0 to t by 2, if you see, from the interval 0 to t by 2, St is minus 1, St is minus 1, and phi 1t is 1 by root t. So minus 1 into 1 by root t, it is integrated from 0 to t by 2. The result will be this into t by 2. And then in the interval t by 2 to t, so I am splitting this 0 to t into two intervals, 0 to t by 2 and t by 2 to t. In the interval t by 2 to t, St is minus 2 and phi 1t is minus 1 by root t. So minus 2 into minus 1 by root t gives 2 by root t. So plus 2 by root t into t by 2, because again it's an integration from t by 2 to t, you will get t minus t by 2, that is t by 2. Now this will be equal to, root minus root t by 2, because this root t and this t becomes minus root t in the numerator, rather root t in the numerator, negative sign is here and 2 is here, and hence this result will be minus root t by 2 plus this result will be 2 cancels, and you will get just a root t, which means that S1 is root t by 2. So we have got S1. Now let's find out S2. Let's find out S2 now. So similarly, S2 will be St into phi 2 conjugate. Again, phi 2 being real, I just write phi 2 dt 0 to t. And the result will be, you can see that S2 again from 0 to t by 2, S2 is minus 1. Sorry, from 0 to t by 2, St is minus 1. So minus 1 into 0 to t by 2, phi 2 t is minus 1 by root t. So minus 1 by root t, and 0 to t by 2, when you integrate, you get t by 2. And plus, of course, t by 2 to t, St is minus 2, and t by 2 to t, phi 2 t is minus 1 by root t. So minus 2 into minus 1 by root t, you get 2 by root t. 2 by root t, and the integration from t by 2 to t will give us a t by 2. So this becomes this becomes 1 by root t, t by 2 gives root t by 2, minus 1 becomes 1, this becomes root t by 2, and this will be root t plus root t. And when you add these two, you will get the result S2 as equal to, so you will get S2 as equal to 3 by 2 root t. And we have already found out S1, it is root t by 2. S1 is root t by 2. So 1.5 root t and 0.5 root t, that is S1 and S2. Now to find S3, we need phi 3. But we see that the signal St can be represented with just these two basis functions. So that means the coefficients S3, S4 onwards all are zeros. We don't have to bother about them. Of course, I have formulated the example like this. As I said earlier, I will say that again. For the moment, and from the perspective of this course, we don't have to worry seriously about how these basis functions are obtained. There are methods for that, but we will not worry about that right now because it is not of direct relevance to the points that we are discussing. So coming back to this case, S of t can be, the signal can be represented with only these two basis functions and these two coefficients, of course. So S1 phi 1t plus S2 phi 2t is all that is required to represent the signal S of t. That means S1 is root t by 2 and phi 1t plus 3 by 2 root t phi 2t. S3 onwards, even if you had a phi 3 and if you did st into phi 3 and then integrated from 0, the result would have been 0. That means S3, S4, S5 onwards will be 0. So you can see that this is indeed the case. So again, phi 1, quickly recalling, phi 1, this was, sorry, phi 1 was this 1 by root t minus 1 by root t. So if I multiply this with root t by 2, if I multiply phi 1t with root t by 2, I get 1 by 2. And since from t by 2 to t, when I multiply the root t by 2, I will get minus 1 by 2. So 1 by 2 from 0 to t by 2, this is the result of phi 1t into root t by 2. Now phi 2t, phi 2t was minus 1 by root t, and when I multiply phi 2t with 3 by 2 root t, if I do this, you can see that you will end up getting minus 3 by 2. You will end up getting minus 3 by 2. That is phi 2t into 3 by 2 root t will be minus 3 by 2. Now if you add the two, because this says that if you add the two, you should get S of t. So if we add the two, what happens is that from 0 to t by 2, so I'll write the sum here, the sum of these two functions, it should give me S of t. So if I add the two, from 0 to t by 2, 1 by 2 minus 3 by 2, that will give minus 1. 1 by 2 minus 3 by 2 is minus 1 because minus 1.5 plus 0.5 is minus 1. And from t by 2 to t, it is minus 1 by 2 plus minus 3 by 2. So that should give us minus 2. And this is exactly the signal. This is exactly the signal S of t. So you can see that S3, S4, S5 onwards, you don't need the remaining basis functions, the remaining functions that you have in the set. It's enough if you have only these two. With these two, it is possible to represent the signal. So now what we have to note, because this was also hinted by me earlier, the signal S of t is now completely described by the signal S of t. This signal is completely described by its two coordinates S1 and S2, where S1 is, just now we saw that S1 is root t by 2 and S2 is 3 root t by 2. It's completely described by these two coordinates, which means that the signal s of t can be visualized as a vector with two coordinates. And these coordinates, it is completely described by these two coordinates as long as we know the two basis functions. And we agree upon the basis function at the beginning of the discussion itself. So we don't have to have this now with us. It's enough if we have these two numbers. We can reconstruct the signal. Provided we have the basis, of course, we should be having the basis with us. And as I said earlier, if the basis changed, if the basis were something else, you would have had the same signal, but the coordinates would have been different. So this now implies that we can represent this signal as a vector in a vector space. Now the signal has two coordinates. It was enough if it was possible to represent the signal using two functions from the basis set, and it has two coordinates, which means that the space in which we are going to show, the space in which we can show this signal as a vector has to be only a two-dimensional space. It can be a two-dimensional space because it has only two coordinates, and the basis is represented appropriately here. So you can visualize this as the ax cap unit vector and the ay cap unit vector in terms of Cartesian coordinates. So we have phi1 of t, which plays the role of a unit vector here because its norm is 1, energy is 1, and it is orthogonal to phi2t, whose norm is also 1. So you can visualize that these play the equivalent role of ax cap and ay cap, which they play in the Cartesian coordinate system. And if I mark root t here, 2 root t, root t, 2 root t, the coordinate s1 will be here, root t by 2, somewhere here, root t by 2, and s2 is 3 root t by 2, that is 1.5 root t, that will be somewhere here, 1.5 root t, which means that the signal st, which is now being seen as a vector, is here on our vector space. And this vector space is given a special name because since we are showing signals on this vector space, we call it as the signal space. So we are actually showing the signal s of t on this signal space as a vector. So this is that signal. So I can write this as equal to s, which is root t by 2, 3 root t by 2. And just to quickly show another example using the same basis, suppose we had a signal. This is a much simpler one compared to the signal st that we had been discussing till now in this example. Suppose we had a signal s of t like this. This is a different signal, let's say. We had a signal like this, let's say. -1 plus 1. Now, if you work out these steps, which not necessary, by visualization also we can solve this problem. S of t, if I were to express in terms of a series representation using the same orthonormal basis that we have with us, S of t will be minus root t phi 1t, because you can see that the phi 1t that we have, if you just multiply it with minus root t, you will get the s of t that we have now here, the new s of t. And S2 will be 0, S3 will be 0, S4 will be 0, and so on and so forth. So the S1 here is this, and S2 is 0. So if I represent this now in this signal space, it will be minus root t is this somewhere here. Minus root t will be somewhere here. And this will be its S1 coordinate, and S2 coordinate is 0. So S2 coordinate being 0, you have it somewhere here, which means that the signal, this signal S, is this itself, because S1 is minus root t and S2 is 0, which is minus root t 0. So this is an example which tells us how a signal can be expressed, or a signal can be represented as a series expansion using orthonormal basis, and consequently how we can visualize that as a vector and represent that on a signal space. Now before we move on, let's calculate what's the energy of a signal and see what's the relation between energy and its representation in the signal space. Now energy of a signal, as you know, is energy of a signal which is of finite energy, of course, otherwise you will not be able to calculate the energy, you will get the energy as infinite. Energy of a signal which is of finite energy, and say it is of duration 0 to t, existing in 0 to t, is this. And we can write this as, since we are now familiar with the series representation, we can write this as so this is st into s conjugate t. This sj and this phi j and this summation stands for st. Sk conjugate, phi k conjugate, and this summation stands for s conjugate t. The product is here like this. And if I can take these terms out of the integration, because these are numbers. So j1 to n, k1 to n, sj, sk conjugate. And this integration, in the integration you will have this, and we have seen this result to be the Kronecker delta earlier, which means that this result will be, one of the summation becomes redundant because this is 0 whenever j is not equal to k. So only the summation where j and k are the same, that is all that is relevant. So one of the summation becomes redundant, and the result can be expressed as this. Because this is 1 whenever j is equal to k, and whenever j is equal to k, this will be just its magnitude square, and as I said, only one summation required. So we now have a connection between the representation of a signal as a vector in the signal space and its energy. So the energy of the signal s of t is equal to the sum of the magnitude square of the signal's coordinates. And this is, if you relate this to the conventional linear algebraic, the linear algebra terminology, you can see that what you have on the right hand side is the squared distance or square magnitude of the vector, and this is called as, or this can, you can easily see that this is the generalized Parseval's identity. This is the generalized Parseval's identity, and the series representation of S of t that we have been discussing so far is called as the generalized Fourier series representation. So with that, we will end this example, and we will proceed further with our discussion in the next lecture.